Hello everyone. So, we will continue with the course testing of functional and technical textiles. Now, let us first see what we have already covered in this course. Here in this course we have already covered the testing of functional textile part, then we have started testing of technical textiles segment, and in this segment we have already discussed testing of fiber reinforced composite material. After finishing that, we have discussed testing of filter fabrics. Now, we have completed that segment, and today we will start testing of geotextiles. So, first we will try to understand what is geotextiles, what are their functions, and then we will discuss various test methods for geotextiles. So, geotextile testing are of different types: tensile, puncture, compression, hydraulic characteristics. So, if we try to categorize the geosynthetics, that means geosynthetics are the material which are used for civil engineering construction related to soil or related to any other construction. So, this geosynthetic products can be categorized in terms of geogrids, geonets, geomembranes, geotextiles. The part which we will cover here, geocomposites, geobag or geotubes, geosynthetic clay liner, geocell, which is 3-dimensional confinement, prefabricated vertical drains PVD, and there are different other materials. But in this course our main focus will be on testing of geotextile products. First, let us try to understand what are the different functions of geotextiles. So, if we understand the functions, then we can assess the needs and types of the testing. First is the filtration, which is extremely important function, where the geotextile has to restrict the soil or sand particles, but at the same time it should allow the water to flow through. So, for that we need to understand the filtration behavior. Next function is the drainage. It is also a very important function, where geotextile needs to drain out the excess water, so that accumulation of water is not there in a particular place, and if accumulation is there, then the strength of the structures, that is soil structure, will be dropped. So, the drainage behavior is extremely important. Third, another important characteristic is reinforcement characteristic. the geotextile is used to reinforce the soil structure. We will see as the moisture content in the soil increases, the soil strength reduces. So, geotextile is used to reinforce the structure. Next function is cushioning. When the load is applied or vertical pressure is applied on the structure, geotextile has to absorb certain amount of load, so that the structure remains intact. Next function is protection. Protection of the structure, like penetration of water reduces the strength of the soil structure. So, to protect the structure, if we use water impermeable geotextile, then the strength of the structure will be intact. Another most important function of geotextile is the separation. If we see for any construction like a road, railway track, this type of constructions, the soil layers are of different type. At the bottom, which is shown here by the brown color, if it is subsoil, soft soil, and after that if we use the gravels of stones of certain size directly, then this stone will penetrate inside the soft soil and the structure will collapse. So, the permeability characteristics of this structure will be lost. Therefore, we need to separate out this two entirely different materials, so that the individual component will have their own identity. So, here geotextile is placed in between these two surfaces and their individual identities are maintained. So, after understanding the functions, that is basic functions of geotextiles, let us first try to see why do you need to test geotextiles. So, first need is that to identify the product. So, we have say n number of products, we need to apply particular geotextile material for a particular use, where we need particular strength or particular thickness or maybe any other characteristics. So, to identify that we must test the product. Next is that to select appropriate material for the product as per the design specification and regulation. So, our targeted product is there as per the design specification or as per the regulation. So, for that product we need to select raw materials, and for that we need to test them. Next requirement is that the quality control during production. We must test the material during production to achieve required product. Then for quality assurance of the product we need to test, then to assess the suitability of a product for a particular application. So, there are different applications and those applications will require different products of different specification. So, for that we need to test the material. Now, when to test geotextile? For any project, for any civil engineering project, the design engineer must check the required specifications of geotextile material. Without knowing proper specification, it is very difficult to select correct geotextile for any specific project. Suppose a particular project requires a filtration characteristics, there the strength may not be required. So, we must test the material as per the requirement. It is necessary to conduct test on geotextile from an independent laboratory. Why is it necessary? Because the supplier will also try to project the product with the positive attributes. So, we need to get the material tested from an independent laboratory to get correct picture, because after using geotextile, if it fails, then not only the geotextile will fail, total structure will be collapsed. Generally, test results are supplied from the manufacturer. This data sheet provide minimum average roll value MARV for quality control only, but actual test data we have to get from an independent laboratory. Considering environmental impact, geotextiles should be collected from the project site. The test which we normally do in isolation, that may not be suitable for most of the geotextile testing. So, we have to get the sample collected from the exact site, and then the sample should be tested in the laboratory. Now, there are standards for collection of test specimens. So, these standards are ASTM D 4354, which is standard practice for sampling of geosynthetics for testing. Then ISO 554, which is specifying the standard atmosphere for conditioning and or testing specifications. ISO 9862, geotextile sampling and preparation of test specimen. So, during production and construction time, test specimens are collected at specified interval. The number of specimens to be collected for testing is given in the concerned standard. So, we have to collect the specimen from the site. So, there are two different types of test which are conducted on geotextiles. One is called index testing or in isolation test, which actually we test in the laboratory condition. So, only the tests are performed on geotextiles. Next is that it is called performance test. What is that? The performance tests are performed along with site specified soil and conditions. So, index test will only give an idea and comparative value between the geotextiles which is good or which is bad comparatively, but the better geotextiles as per index text may not perform well in performance test, because in performance test we have to test along with the site specified soil and site specified condition. So, there are different types of tests conducted on geotextile materials. These are physical testing, mechanical test, hydraulic test, endurance test, degradation test. So, we will discuss each and every methods in our next discussion. In physical test, if we see physical properties of geotextiles, mainly specific gravity, mass per unit area, thickness and stiffness. These tests are coming under physical properties of geotextiles. First, let us see how to test the specific gravity. So, this specific gravity is actually defined as the material's unit volume weight, that means mass per unit volume, that is density, to that of distilled deaerated water at 27 degree Celsius temperature. That means ratio of mass per unit volume, that is ratio of density of material to that of distilled water. So, there are different methods of measurement of specific gravity. The method is pycnometer method or density bottle method, which is used to determine the specific gravity of geotextile material. So, pycnometer or density bottle method, they are very commonly used for measuring the specific gravity. Floating sinkers are used for testing materials. So, typical values are, these are the typical values of specific gravity for comparison, like steel 7.87, rock 2.4, soil 2.7, like this, polyester 1.22 to 1.38, PVC 1.69, nylon 1.05 to 1.14, polyethylene 0.902, 0.96, polypropylene 0.91, like this. So, we can test the specific gravity using pycnometer method. Next characteristics is mass per unit area. We can test mass per unit area by many standards like BSEN 9864, BSEN 965, ASTM D 5261, ASTM 2001, 2.13, any method we can use, and this method if we follow, we can get the mass per unit area of geotextiles. So, here what we have to do, we have to cut typically 5 to 10 samples, each of having area not less than 10,000 square millimeter. That means, if we want to get the specimen. So, minimum size should be 10 centimeter by 10 centimeter. So, that is the test specimen size, and combined total area of not less than 100,000 square millimeter. So, for geotextile we need to test larger size. So, at least such 10 samples should be there, measured the dimensions without applying tension. So, we have to test in relaxed condition, and then we have to take the mass of this specimen with an accuracy of 0.01 gram, and from there we can calculate the mass per unit area, total mass by total area. So, we have to add all the specimens area and we have to add all the specimens mass to get the mass per unit area, and reporting the mass per unit area with an accuracy of 0.1 gram per square meter. Basically, the importance of mass per unit area is that the cost of geotextiles, they are directly dependent on the mass per unit area. Next is the thickness. So, we can use all these methods like BSEN ISO 9863-1, ISO 9863-2, BSEN 964-1, ASTM D 5199, Australian standard AS 2001.2.15. So, any of the methods we can follow. So, thickness is given by the distance between upper and lower surface of geotextile when we apply a pressure of 2 kilopascal, and it's normally it is expressed in terms of millimeter. And for geotextile, if it is oven geotextile, the range is typically around 0.25 to 1 millimeter the thickness, and non-oven geotextiles it is around 1 millimeter to 10 millimeter and above. So, very thick non-oven geotextiles are used, but if it is oven it is around 0.25 to 1 millimeter thickness. Thickness of geogrid and geomembranes which are not so compressible, the pressure which is applied is of the order of 20 kilopascal. For geotextile we use 2 kilopascal, for geogrid and geomembranes we use 20 kilopascal, and compressibility is the change in thickness with pressure. So, we can test compressibility also if we change the normal pressure and record the thickness of the material. Next important physical characteristics is the stiffness. What is that? Stiffness is measured of interaction between the geotextile mass and the bending stiffness, and which is expressed in terms of milligram centimeter. So, where the bending stiffness and mass of geotextiles are incorporated. For same bending stiffness, if the mass of geotextile is changed, then the stiffness value will get changed. So, that is why in the equation both the stiffness value and the mass per unit area, these are incorporated. How do we get the stiffness value? bending stiffness value we get when a 25 millimeter wide strip is made to incline at an angle of 41.5 degree under its own weight and the overhanging length L is measured. It is as per the Searle stiffness tester, okay, which we have learnt in other course. Here also in this course we have discussed in functional textile segment, and we can measure the overhanging length L and stiffness value in milligram centimeter we can calculate by using the formula L by 2 cube multiplied by mass per unit area, and this stiffness value is very important for design application. Like subgrade soils, severe value, severe, what is severe? Severe is California bearing ratio, we will discuss in detail, which represent the strength or hardness of soil. So, higher the severe value, that means harder will be the soil. So, if severe value is less than 0.5, that means it is a soft soil. In that case we require stiffer material. So, higher stiffness means higher, more the stiffness of the material. So, if it is 0.5 or less, we require 15,000 to 25,000, 1 to 2 severe value of soil subgrade it is 5,000 to 10,000, and more than 2 it is typically around 1000 stiffness. So, for soft soil we need stiffer geotextile, so that the structural integrity is maintained. We can have flexible geotextile if the subsoil is strong enough or hard enough. The property is important in field workability requirement, as I have just discussed. If the soil is very poor or severe value is very less, we need stiffer geotextiles. After physical characteristics, now we will start the mechanical properties of geotextiles. In mechanical properties, there are tensile strength, fatigue strength, seam strength, bursting strength, impact strength, tear strength, compressibility of geotextiles, frictional behavior of geotextiles, puncture test, pull out test, and direct shear test. So, we will discuss all these test methods one by one. First, let us start with the measurement of tensile strength. So, there are different types of tensile strength. First is wide width tensile strength, it is as per ASTM D 4595 and ISO 10319. Then very wide width tensile strength, next is grab tensile strength as per ASTM D 4632, then narrow strip tensile strength, which is as per ASTM D 4751, third Swen seam strength of geotextile. This is actually tensile strength, but in the seam portion, because geotextile when we are laying we must incorporate stitches, and the strength of the stitched portion is evaluated by this method. So, Swen seam strength of geotextile is measured as per ASTM D 4884 and ISO 13426 method. Another tensile strength is in terms of trapezoidal tear strength test. Although we can place this in different categories, but as the test procedure is similar to tensile strength, we can discuss here also. First, we will discuss the wide width tensile test, where we must prepare a specimen of size 200 millimeter wide. So, 20 centimeter wide and 10 centimeter length in each warp and wave direction. If it is oven, so we need to test wide width tensile test, because when geotextile is laid under the ground, this wide width tensile strength is actually simulates the in situ condition. Machine strain rate is 10 plus minus 3 per minute, that is 10 plus minus 3% of the breaking elongation. The reason for selecting wide width sample is that geotextile, especially non-woven geotextile, achieve high Poisson's ratio when we test the narrow width test. So, to reduce the Poisson's ratio, we try to test in wide width tensile test. So, we have to mount the sample centrally, and tensile strength is measured by observed breaking force in kilonewton by width of the specimen. So, F b by W kilonewton per meter. Here we do not measure in terms of Newton per tex or like that, as we test normally for narrow width test, but in wide width tensile test we expressed in terms of kilonewton per meter. This is the schematic diagram where width of the geotextile is 200 millimeter and length of the specimen is 100 millimeter. Actual specimen length will be more than this, but gauge length, initial gauge length is 100 millimeter. So, due to this wide width, the Poisson's ratio is restricted, and this value, the result which we get here from wide width tensile test, it simulates the actual field condition. In some application we may need very wide width tensile strength. So, where the width of the specimen is as high as 1 meter. So, we have to design the jaw accordingly, and the length is half of that. So, half meter, 1 meter by half meter, it is the actual test specimen size. We sometime test the geotextile in narrow strip tensile mode also, where size of the strip is 75 millimeter by 25 millimeter, strain rate is 300 millimeter by minute, tensile strength appear to be less than the wide width tensile strength here. And this test, it is for index testing only, it is not recommended for design value. So, the value we cannot use for designing the geotextiles, for using in any project. So, if we see the comparative stress strain curves for different types of geotextiles, here it is a monofilament woven fabric and next one is multi-filament woven fabric. So, monofilament woven fabric, although the breaking stress is less than the multi-filament woven fabric, but the monofilament woven fabric has got higher modulus. Multi-filament woven fabric has relatively lesser modulus than monofilament, but this multi-filament woven fabric has got very high tensile strength. Next is the slit film woven fabric, which has lesser strength, but it has got high modulus value. And as far as non-woven geotextiles are concerned, the needle punched non-woven geotextile has got least modulus, and after certain strain the fabric starts showing of stress due to reorientation of the fibers, whereas heat bonded non-woven fabrics, they have relatively higher modulus. So, these are the different curves, stress strain curve. This curve in the left side, which shows the initial tangent modulus. So, this is actual curve, stress strain curve. If we take the tangent and from there we can calculate the initial tangent modulus. We can also calculate the offset tangent modulus, which is required for geotextile design for any construction. This offset tangent modulus is that it is a modulus for any offset value, for any particular stress value or strain value, we can get the tangent at that point. Another important parameter is the secant modulus. This is again the modulus between the origin and any specific point. So, at say particular strain value, desired strain value, if we want to know the secant modulus, so we can calculate by drawing the straight line between origin and at that point. So, this curve shows the comparative values of non-woven heat bonded sample 1, this is non-woven heat bonded, sample 2 non-woven needle punched fabric, this is non-woven needle punched fabric, and woven monofilament fabric. So, this comparative curves showing the modulus values and tensile characteristics, and it is important to study the comparative values to select the specific material for a particular application. Where we need strength, we may go for specimen 3, that is woven fabric. Suppose we need certain elasticity, certain extensibility of a structure, we may go for specimen 2, that is needle felt fabric, like that. Next characteristics is that Grab tensile test. So, this is construction survivability test. It is not only the tensile test, this test will give idea about the survivability of the structure, how the structure will survive during application of load for long time, especially for separator applications in pavement. Here now let us discuss here, this is geotextile and we have say stones, and these are the contact points, gripping points we can say. Now, when load is applied vertically, this stones will try to move sideways. Having these 2 points gripping point, the geotextile will be stretched in lengthwise direction, and the gripping point is not like wide width or narrow width tensile testing. Here gripping points are much less than the actual width of the material. Suppose this is the total material width and this grip point will be like this, this is the small grip point, this is the point, this is here is a, and they will be pulled apart, and this is actually simulated by the Grab test, where we use this geotextile for separation application. The 25 millimeter narrow width grips are used here. So, this width of the grips are 25 millimeter and width of the specimen here is a 100 millimeter. So, 100 millimeter width specimen and it is gripped by 25 millimeter wide jaw, and rate of loading is that the strain rate is 300 millimeter per minute. The test depends on filament interaction in geotextile. For non-woven geotextile, the effects are more than woven geotextile. So, for non-woven, if we use and if we compare the Grab test and the strip test, the effect will be more in case of non-woven geotextiles. Tensile strength is expressed in terms of kilonewton here. It is not like wide width tensile test where we express in terms of Newton per meter or kilonewton per meter. As the sample is partially clamped, so this sample is not clamped fully, as I have mentioned. Out of 100 millimeter width, we grip only 25 millimeter at the center. The stress here is not propagated in entire width of the specimen. So, basically the stress will be concentrated mainly on the central zone, but it will be assisted by the ungripped zone. Now, let us try to see the analysis. The Graft tensile strength is required to design the geotextile for separation. So, this is for separation purpose here. When pressure is applied to the upper stone, so when it is applied, it spreads the two lower stone laterally. So, these two lower stones will be laterally actually move away. As a result, tension is mobilized in the geotextile. So, these are the gripping point, the tension will be mobilized and it is simulating the Graft tensile strength. So, here it is a actual field condition, and after the stones are moved, this is the condition. Now, this is the analogous Graft tensile strength. These are the gripping point. Now, let us see the analysis here. D is the average diameter of stone, L1 is the initial grip length, this is the initial grip length here. Now, assumption here is that the stones are spread at equidistance. So, distance between these stones are half of the average diameter. So, d by 2. So, initial grip length will be, this is d by 2 plus d by 2, these 2 points are grip points. So, total grip length, initial length will be 3 by 2 d, and final length will be when this upper stone is actually taking space in between the lower stones. So, the gripping point has been stretched from this point to this point here, that means total elongated length will be d by 2 plus d plus d by 2. So, it will be 2d is the total length after elongation, that is the final length. Now, if we consider that there is no slippage between the fabric specimen, that is geotextile specimen, and the stone, and there is no crushing of stone. So, the maximum strain in geotextile can be expressed as the epsilon equal to L f final length minus initial length by the initial length multiplied by 100. So, what was the final length? So, d plus d 2d minus 3 by 2 d, that is initial length, by 3 by 2 d. So, effectively it will be 1/3, and if we express in terms of percent, it is 33%. So, with this condition, simplified model, we can see the extension here is 33%, and there was one empirical equation which is proposed by Giroud in 1984, which says that required grab strength of material, that is we are talking about the required strength in the structure, it is not the material strength, it is a required strength which is equal to applied pressure from the top AP multiplied by dV. What is dV? It is a mean or maximum volume of void diameter. Maximum void diameter is that it is a dV, which is approximately equal to 0.33 times diameter of stone dA. Okay. So, AP multiplied by dV square multiplied by strain epsilon. So, this will give the required grab strength of material. Now, let us try to see one practical problem to calculate the required grab strength of geotextile. The problem is that a tire inflation pressure is 450 kilopascal. That means, the tire inflation pressure shows that that tire will impart the vertical pressure of that amount 450 kilopascal, that is a vertical pressure. Average stone diameter is 30 millimeter. Assume the geotextile is placed beneath the stone base course, calculate required grab strength of the geotextile. So, assuming here 60% of the total ultimate grab strength will be mobilized. So, only 60% will be mobilized. Now, let us see here total ultimate grab strain is 33%, because we have already seen here we are not considering any slippage. So, 33% is the strain percent and mobilized grab strength is 0.33 multiplied by 60 grab strain. So, that total whatever grab strain was there 60% will be mobilized, that means 40% slippage was there. The effective strain will be 0.33 multiplied by 0.6, it is 0.198, that is the strain value, and the diameter of stone was 30 millimeter, that is 0.03 meter, and void diameter, maximum void diameter is 0.33 multiplied by 0.03. So, required strength of geotextile, that is grab strength of geotextile is 450 is the pressure as per the formula proposed by Giroud. We can calculate, it is coming out to be 8.73 Newton. So, that is the required grab strength of the geotextile. So, if we know some given condition, so we can calculate the required grab strength, and then what we do, we will take the specimen actual geotextile sample, we will test the grab strength, and if it is more than this required strength with some factor, then we can accept that geotextile, otherwise we can reject. So, next we will discuss the trapezoidal tear strength test, but this will continue in the next class. Till then, thank you for patient hearing.